Hi everyone. Hi everyone. Welcome to the Student the Brand. So in the previous we live class, you can check. So if you see in the previous live class, I explained about until light reflection and diffraction. So you can check. Okay, 1 minute. Yes. So I won't forget. Definitely, you'll remember. You'll be always your student from Kerala. Yeah, of course, definitely. Okay, so I hope you got to know until this one we discussed. So you can check once here. We discussed about light reflection and diffraction. So anyway, introduction is common only. Myopia, myopia, myopia. Myopia, myopia, myopia. Near distance we can see ya, far distance we can see ya. Myopia, myopia, myopia. Near distance we can see ya. Myopia, myopia, myopia. Near distance we can see ya. Far distance we can see ya. Myopia, myopia, myopia. For that correction we are using. Bro, what bro? For that correction we are using concave lens, concave lens, concave lens, concave lens. Myopia, 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 myopia. Near distance we can see ya, far distance we can see ya. Hypermetropia, 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 hypermetropia. Far distance we can see, near distance we can see. Hypermetropia, 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 hypermetropia. Far distance we can see, near distance we can see. For the correction, we are using convex lens, convex lens. Hypermetropia, convex lens, hypermetropia, convex lens, hypermetropia, convex lens. So now, like that. So we are singing one more song. That is New Cartesian sign convention. All distance measured from the pole. Distance positive along the instant trace. Distance negative opposite to instant trace. Distance positive above the principal axis. Distance negative below the principal axis. New Cartesian sign convention. All distance measured from the pole. Distance positive along the instantaneous. Distance negative opposite to instantaneous. Distance positive above the principal axis. Distance negative below the principal axis. New Cartesian sign convention. New Cartesian sign convention. All distance measured from the pole. Distance positive along the instant trace. Distance negative opposite to instant trace. Distance positive above the principal axis. Distance negative below the principal axis. Okay, so welcome to the student independent command. So just we are entering into the second hour of explanation. That is nothing but refraction. So till now we discussed about reflection. So reflection is completed. Now we are going to discuss about refraction. Okay. So refraction is nothing but, so here you can observe until here you can observe. Okay. So now you can check here. So in the morning, in the previous class, we discussed until here. Okay. So object is at infinity, image will form at focus. Object is at infinity, image will form at focus. So one light ray empty. So how many light rays are required to form the image of the object? Minimum 2 light rays are required to form the image of the object. How many light rays are required to form the image of the object? Minimum 2 light rays are required to form the image of the object. How many light rays are required to form the image of the object? Minimum 2 light rays are required to form the image of the object. Object is placed at infinity, image will form at focus. So nature of the image is real and inverted and highly diminished. Object is placed at infinity, image will form at focus. So nature of the image is real, inverted and highly diminished. Coming to the object is placed beyond center of curvature. Image will form between C and F. Object is placed beyond center of curvature. Image will form between C and F. Nature of the image is real and inverted. near real and inverted and diminished image. Compared to the object, image size is decreased. So here in this case, object is placed at center of curvature. Object is placed at center of curvature. Image also will form at center of curvature only. Object is placed at center of curvature. Image will form at center of curvature. So nature of the image is real and inverted, and size of the image is same size. So here object is placed between C and F. Object is placed between C and F. Image will form beyond center of curvature, beyond center curvature. So nature of the image is real inverted and size of the image is enlarged. And coming to the next one. So hi everyone, welcome to the class. Here object is placed at focus, image will form at infinity, nature of the image is real and inverted, highly enlarged. So here object is placed between F and P. So image will form behind the mirror. Nature of the image is virtual erect and enlarge. Very very important. So image will form virtual erect and enlarge. Enlarged image will form. Virtual erect and enlarged image will form, because so image will form. So virtual erect and enlarge. So virtual erect and enlarge image will form behind the mirror. So nature of the image is virtual erect and enlarge. I hope you can understand. So these are the image formations by concave mirror. So next one, image formation by convex mirror, will discuss. So in convex mirror only two cases are there. I will explain now. Convex mirror only two cases. So convex mirror only two cases are there. We'll discuss those two cases. Convex mirror, those two cases we'll discuss. Okay. So object is placed in concave mirror. You can see. Okay, done. So object is placed. So here I'm considering convex mirror. So image formation by convex mirror. So in this case, only two cases are there. In this mirror, only two cases are there. So for one case is object is placed at infinity. So one case is object is placed at infinity. I'm taking. So I'm taking the convex mirror like this. So I'm considering here. Like this. So pole. This is a pole. Focus. Center of curvature. Pole focus and center of curvature. Object is placed at infinity. So how many light rays are required to form the image of the object? Minimum 2 light rays are required to form the image of the object. How many light rays are required to form the image of the object? Minimum 2 light rays. So minimum 2 light rays are required. 2 light rays are required. So 2 light rays are required to form the image of the object. So 1 light ray I am taking like this. So another light ray I am taking like this. After reflection you can observe, after reflection those light rays will meet here. See, if you are extending like this, image will form at focus. Image will form at focus. Object is at infinity. Object is at infinity. Image will form at focus. Object is at infinity. Image will form at focus. Okay. Object I am taking. Object is at infinity. Object is at infinity. Okay. Object is at infinity. Image will form. Image will form. So object is at infinity, image will form at focus. Nature of the image is real and inverted. Virtual erect, because virtual image will form here. Right? Virtual image will form. So nature of the image is virtual erect and highly diminished. Virtual erect and highly diminished. Once again, object is placed at infinity. Object is placed at infinity. Image will form at focus. Image will form at focus. What is the nature of the image will form? Nature of the image virtual erect and highly diminished. Virtual erect and highly diminished. Coming to the next one. So only two cases I said, right? Only in convex mirror only two cases are there. Convex mirror only two cases are there. Convex mirror only two cases are there. So one is this one. Another one I am taking. Another one, if you are considering like this, if you are drawing here, if you are drawing like this, okay. So I'm considering here. Okay. So object is placed anywhere between pole. So focus and center of curvature. Object is placed between anywhere between pole and infinity. Object is placed between anywhere between pole and infinity. How many light rays are required to form the image of the object? Minimum 2 light rays are required to form the image of the object. So I'm considering here. One light ray I'm taking. Hi everyone, welcome to the class. So one light ray I'm taking here. Another light ray is incidenting at the pole. It will be reflected. So if you are extending this reflector light rays, okay, so their image will form here. So the image will form here. Okay, so the image will form between F, P and F. The image will form here. What type of image will form? Virtual erect and diminished image. Once again, object is placed between P and infinity. Image will form between P and F. So nature of the image is virtual and erect. And size of the image is diminished compared to the object. Image size is decreased. Compared to the object, image size is decreased. I hope it is very clear to you all. Once again, convex mirror. So it is also known as diverging mirror. Convex mirror is also known as diverging mirror. Okay, convex mirror is also known as diverging mirror. Only two cases are there. In convex mirror, only two cases are there. Object is placed at infinity. Image will form at focus. What is the nature of the image? So nature of the image is virtual erect and highly diminished, because point size image will form at focus. And one more thing, so object is placed between P and F. So here this case, object is placed between P and infinity. So object is placed between P and infinity. Image will form between P and F. So what is the nature of the image? Virtual erect and diminished. Compared to the object, image size is decreased. So that's why it is called virtual erect and diminished. Object is placed at infinity. First case, image will form at focus. So nature of the image is virtual erect and highly diminished. Here object is placed between P and infinity. Nature of the image is between P and F. Image will form between P and F. Nature of the image is virtual erect and diminished. So image size is diminished. Okay. So this is about convex mirror. So now we will discuss one more. So actually related to this one, questions will be there. questions will be there. Few questions are there. Those we will discuss related to convex mirror. Okay, terms related to concave and convex. And one more thing, very very important. Radius of curvature is the twice of the focal length. So radius of the curvature is the twice of the focal length. So that is very very important. I will discuss that one. Now you can see radius of curvature is the twice of the focal length. Radius of curvature is the twice of the focal length. Radius of curvature is the twice of the focal length. So here I can see. I remembered. You said when I'm taking class. So don't shout too much like that. You mentioned, right? Reena Datta. Yeah, I remembered. Reena Datta. Yes. When I'm taking class, very like with very intensive manner. I notion. Hi. With intensive manner you said that day. So still I remember in middle of the serious class, suddenly you said that word. So after that again I started. So I thought in a normal mode. Uh, yes. So definitely. Now you are considering next one. Next one I am considering here. Convex mirror is completed. So if you are taking the concave mirror like this, I'm taking the concave mirror like this. I'm taking the concave mirror. I'm taking the concave mirror. So here, so pole, focus, center of curvature, pole, focus, and center of curvature. Okay, so I'm considering here. I'm considering here. I'm considering here. Okay, so I'm taking here. I'm taking here. This is the pole focus. See, how many? So I'm taking one light ray. I'm taking one light ray like this. After a reflection, it passes through the focus. So I'm taking one light ray. After reflection passes through the focus. After reflection passes through the focus. So here I'm considering. After reflection passes through the focus. So this is the incident ray and this one is the reflected ray. Incident ray and reflected ray. Incident ray and reflected ray. This is the incident ray and reflected ray. So it is passing like this. I'm taking like this. Okay, if you draw the normal, so normal line will pass through the it will pass through the center of curvature. Normal line it passes through the center of curvature. Okay, so the angle between, so this one is the angle of incidence and this one is the angle of reflection. Angle of incident and angle of reflection. Angle of incident and angle of reflection. So we know loss of reflection, angle of incident is equal to angle of reflection. So that's why I'm taking this one. So if you are taking the general alternative angles are equal, so this angle and this angle are equal. Suppose I am taking, this is some x value I am taking, this is some y value. Suppose we can take that just for assuming, we can assume. So this theta I am taking suppose z. So here x equal to y, because from loss of reflection x equal to y. From loss of reflection, by comparing by with the help of loss of reflection, we can see x equal to y. X equal to y. Yes or no? X equal to y. So from loss of reflection, angle of incident equal to angle of reflection. So this x and y z. So for our convenience, for understanding purpose, so I am giving these points for understanding purpose, for understanding of the phenomena. Just I given. So here you can see, here I'm considering angle of incident equal to angle of reflection, angle of incident equal to angle of reflection. Okay, so now this x and y are equal. See, so we know according to the alternate angle set rule, if this angle and this angle are equal, right? So alternate angle are equal, then so if this angle, see, this is the x and this is z. So x equal to z. X equal to z. Observe carefully. So I am taking x equal to y. X equal to y. Anyway, we know angle of incident equal to angle of reflection. So with that phenomena, if you are taking angle of incident is equal to angle of reflection, Angle of incident is equal to angle of incident is angle of incident is equal to angle of reflection. Angle of incident is equal to angle of reflection. So with that, so I'm taking angle of incident equal to angle of reflection. Now, so this is the this I am considering. So this angle and this angle, x and z are equal. X and z are equal. Why alternatives angles are equal? So if you are taking this a triangle, so right angle triangle. So like this is the z rule like this. So center passing through that one. So I'm taking this is AM. AM I'm considering. So yes. So AM is the ray. AM is the ray. This is the center of curvature, and this is I'm taking the pole. So at the center of curvature, this angle, here angle, and this angle both are equal. Okay, alternatives angles are equal, right? Okay, so now you are taking x and z are equal. X and z are equal. Then here, if x and x equal to y, x equal to y, x equal to z, then z equal to y, right? Y equal to z, y equal to z. That means so this in a triangle, two angles are equal. So this is the triangle. Okay, this is the triangle. In a triangle, two angles are equal. That is called isosceles triangle. To the if you are taking this CF equal to FM, CF equal to CF equal to FM, CF equal to FM, CF equal to FM, CF equal to FM. Right? This side is equal to this side. So normally in this case we are taking paraxial rays, paraxial rays. And so one more, first one is paraxial rays, second one I will explain these two rays, marginal rays. Okay, so the rays which are very close to the principal axis, the rays which are very close to the principal axis, those are called paraxial rays. The rays which are very close to the principal axis, those are called paraxial rays. The rays which are away from the principal axis. So I'm taking here concave mirror like this. So if you are taking very closer, okay, so the rays which are very close to the principal axis, okay, so if you are taking these are very close to the principal axis. So which are the axis? So I'm taking here. These rays are very close to the principal axis. These rays are very close to the principal axis. Those are called paraxial rays. Paraxial rays. So the rays which are away from the principal axis, those are called marginal rays. Means here we are taking paraxial rays because the rays which are very close to the principal axis only we will take. Okay, the rays which are very close to the principal axis only they will take. So we will take, right? So that's why we are taking the paraxial rays in this case, paraxial rays. So in that manner, so in that case, so here I am taking this M is very close to P. M is very close to P. Then FM. So FM equal to FP. FM equal to FP because this distance is almost, so this point is very close to the P. So then automatically this distance is equal to this distance. So we know if the distance between focus to pole is called focal length. The distance between focus to pole is called focal length. The distance between focus to pole is called focal length. Okay. So the distance between focus to pole is called focal length. So this distance is equal to, see, already we know from isosceles triangle FM equal to CF equal to FM. So this is F, automatically this is also F. So then R equal to, so the distance between center of curvature to pole is called radius of curvature. The distance between center of curvature to pole is called radius of curvature. The distance between center of curvature to pole is called radius of curvature. R equal to 2F. The distance between center of curvature to pole is called radius of curvature. R equal to 2F. I hope you got it. Okay. So this is about radius of curvature is the twice of the focal length. Once again, I will explain. Listen carefully. So here I am considering The light ray is coming from infinity. So after reflection passes through the focus. After reflection passes through the focus. So one light ray. So from angle, from loss of reflection, angle of incident equal to angle of reflection. Angle of incident equal to angle of reflection. From loss of reflection, angle of incident equal to angle of reflection. So this angle and this angle both are equal. This angle and this angle both are equal. Okay. So this one angle equal. So we know according to the alternative Z rule. So if you are taking alternative angle, so x and z. So I given here x and z. So this is the angle. This angle is x. This angle is z. So here x equal to y. X equal to y. X equal to z, x equal to z automatically. So y equal to z. So that's the reason y equal to z. So in a triangle, two angles are equal. In a triangle, two angles are equal. That is called isosceles triangle. So two sides, CF equal to FM. CF equal to FM. CF equal to FM. And one more point, and one more point, and one more point, and one more point, that is, so this point, so light ray, what are the light rays we are taking here? Paraxial rays. The rays which are taking in this case is paraxial rays. Paraxial rays are nothing but the rays which are very close to the principal axis. The rays are very close to the principal axis. The rays which are very close to the principal axis, those are called paraxial rays. The rays which are very close to the principal axis, those are called paraxial rays. Those are called paraxial rays. Here I am taking the paraxial rays. So this M is very close to P. This M is very close to P. This M is very close to P. Then Fm equal to Fp. Fm equal to Fp. Fm equal to Fp. So the distance between F and P, the distance between F and P is focal length. The distance between F and P is focal length. The distance between F and P is focal length. Then automatically, so we know this already, this distance is equal to this distance. So already we know this one. We know this one. So CF equal to FM. Automatically FM equal to FP. 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 So FP equal to small f and CF equal to one more f. So total we are considering. So the distance between center of curvature to pole. The distance between center of curvature to pole. The distance between center of curvature to pole. The distance between center of curvature to pole is called radius of curvature. The distance between center of curvature to pole is called radius of curvature. The distance between center of curvature and pole is called radius of curvature. Radius of curvature. So R equal to F plus F 2F. R equal to 2F. So radius of curvature is the twice of the focal length. Radius of curvature is the twice of the focal length. Radius of curvature is the twice of the focal length. Radius of curvature is the twice of the focal length. R equal to 2F. R equal to 2F. R equal to 2F. So that is about radius of curvature is the twice of the focal length. Okay. So next one. So we'll discuss few more points. We'll discuss about so same phenomena only, concave mirror and convex mirror. Concave mirror and convex mirror will discuss. Concave mirror and convex mirror. So image formations already completed. So till now we discussed about image formations. Okay, now we are going to discuss few more we'll discuss. Okay, so those we can see now. Now, so we can discuss now. So here we are considering uses of concave mirror. Where we'll use concave mirror? So concave mirror used in torchlight, vehicle's headlight. So vehicle headlight, see, we will get parallel beam of light. Torchlight, headlights, and also in solar furnace also we are using this mirror. Solar furnace to convert the sun rays. We are using convex mirror, concave mirror we are using. And dentist to observe the teeth of the patient. Will use the concave mirror to observe the teeth of the patient. Okay, that is about concave mirror. Coming to the convex mirror used as rear view mirror. So why we are using convex mirror as rear view mirror? That is a point. So convex mirror, normally if you see, so why what is the reason behind this? Convex mirror used as a rear view mirror. Normally if you are taking, so this is a concave mirror. This is a concave mirror, concave mirror. So and plane mirror. So plane mirror, concave mirror and plane. This is a concave mirror. I'm taking whenever the light rays are incidenting. Whenever the light rays are incidenting like this. So I'm considering here. So like this it will happen. This is a plane mirror. So extreme position with this only the reflection takes place. With this only reflection takes place. Whereas convex mirror you see. Whereas convex mirror you see. So the region between two extreme reflected light rays, the region between two extreme reflected light rays. So I'm taking here if it is incidenting at the edges and if it is incidenting at the edges, okay. So this much, so this full view, okay. So we can see this much region, we can see this complete region, whereas concave mirror is very small compared to the convex. Even for plane mirror also, the field view is less, the field view is less, the field view is less. So for a convex mirror only the field is more. For convex mirror only the field is more. For convex mirror only the field is more. So the region between two extreme reflected light rays, the region between two extreme reflected light rays, the region between two extreme reflected light rays is called field view. For convex mirror the field is more. For convex mirror the field is more. For convex mirror the field is more. That is the reason. That is the reason. So convex mirror used as a rear view mirror. Convex mirror used as a rear view mirror. Rear view mirror. Rear view mirror. So we can see fully of the tropic. We can see fully of the tropic. Okay. Even if you place, if you stand, if you take in front of the Taj Mahal also, we can see the fully of the object, fully of the Taj Mahal. Even if you are standing in front of convex mirror, we can see full view. And even you can observe in the security mirror. So like buildings are there, building crossings also, there is a red insulation, red color insulation, red color will be there. So big mirror will be there. That is only convex mirror. So we can see the traffic, so around, okay, like that. So convex mirror used is a convex mirrors are used in reflecting surface and used in staircase mirrors and double decker buses also. Security mirrors, it will be used as a security mirrors. And one more question, okay, related to mirrors, okay. So define terms related to spherical mirror. So define pole, center of curvature, radius of curvature, principal axis of aperture. Anyway, we discussed those points. Right? So pole, focus, center of curvature, aperture, and focus, focal length, all those points we discussed. Name the mirror which can give an erect and enlarged image of an object. Name the mirror which can give an erect and enlarged image. Concave mirror, only concave mirror we will give the erect and enlarged image. Last case. So an erect and diminished image. So an erect and diminished image, convex mirror. Erect and diminished image is convex mirror. So an erect and same size, plane mirror. So magnification is positive, +1. Magnification is +1. In which mirror will get magnification +1? Only plane mirror. Only in plane mirror only get only in plane mirror only will get magnification positive. Magnification is positive. Coming to the difference between concave mirror and convex mirror. Difference between concave mirror and convex mirror. Reflecting takes place inward. Concave mirror, if you say, so till now I explained. So you can observe all the image formations. So reflection takes place inward. Whereas convex, reflection takes place outward. Concave mirror forms virtual and see, convex mirror forms both type of images. So real inverted and virtual erect also. Concave mirror. And concave mirror have real focus. After reflection, those light rays are meeting at one point. So concave mirror is also known as converging mirror. So converging mirror. So the focal length of concave mirror is negative. Whereas convex mirror forms always virtual erect and diminished. Convex mirror has virtual focus. So convex mirror is also known as diverging mirror. Convex mirror is also known as diverging mirror. The focal length of convex mirror is positive. So we'll do few questions related to convex mirror, and so later we'll go to the refraction phenomena. So refraction I'll explain. So now we are going to the okay. So now you can see the radius of curvature of spherical mirror. Radius of curvature is given. Radius of curvature is, so radius of curvature if you are taking r equal to radius of curvature of spherical mirror is, radius of curvature is given 20 centimeter. So 20 centimeter. What is the focal length? So focal length they asked. So till now I explained, just now I explained about radius of curvature, relation between radius of curvature. So relation between radius of curvature and focal length, r equal to 2f. R equal to 2f. So now you can take r equal to 2f. I'm considering r equal to 2f. F equal to r by 2. F equal to r by 2. R equal to how much? 20. R equal to how much? 20. 20 by 2. 20 by 2. That is nothing but 10 centimeter. 10 centimeter. So focal length is 10 centimeter. Okay. Next one. We are going to the next problem. Name a mirror that can give, name a mirror that can give erect and enlarged image, erect and enlarged image, erect and enlarged image. Name a mirror that can give erect and enlarged image, erect and enlarged image, erect and enlarged image, erect and enlarged image. So concave mirror, only in concave mirror only, image will be erect and enlarged image. So why do we prefer convex mirror as a rear view mirror in vehicles? Already said. So concave mirror, convex mirror. Why we are using convex mirror as a rear view mirror? Convex mirror as a rear view mirror. Okay, so here convex mirror prefers. So convex mirror always forms virtual erect and diminished image. Virtual erect and diminished image. Okay, so convex mirror. So okay, welcome to the. So convex mirror always forms virtual erect diminished image, virtual erect and diminished image, virtual erect and diminished image. So convex mirror gives the wider field view. It enables us to see the larger view of the topic behind of us. Okay, so we can see. So with the help of this one, we can see the large traffic view, large topic. Okay, whatever it is there, large traffic behind of us. Find the focal length of convex mirror whose radius is 32 centimeter. So radius is 32 centimeter is given. Radius is 32 centimeter is given. Okay. So find the find the focal length of convex mirror whose radius of curvature is 32. So radius of curvature is 32 given, focal length r equal to 2f, f equal to r by 2, 32 by 2, 16 centimeter. Okay, next one. We wish to obtain an erect image of an object using concave mirror, focal length 15. What should be the range of distance of an object from the mirror? What is the nature of the image? Is the image larger or smaller than the object? Draw a ray diagram to show the image formation in this case. So this question is very, very important. This question is very, very important. So focal length is given 15 centimeter. Focal length is given 15 centimeter. So you can see here, I am taking the concave mirror here, concave mirror here. Okay, focal length is 15. Focal length is 15. Focal length is 15. Okay. So focal length is 15. Focal length is given 15. 15 centimeter is given. Okay, so focal length is 15 centimeter, right? So then, if you are placing the object if you place here, this is the pole, focus, center of curvature, pole, focus and center of curvature. If you place the object here, if you place the object between F and P, if you place the object between F and P, one light I am taking like this, it passes through the focus. Another light is incident at the pole, so it reflect. Okay, if you are extending this light rays, the image will form here. Okay, so this is the, so less than 15, focal length is given 15 centimeter. In concave mirror, focal length is given 15 centimeter. So where we have to place the object to get erect and enlarged image. Object must be placed less than 15. Object must be placed less than 15. So here is focal length is 15, less than 15. If you place, image will form behind the mirror. Image will form behind the mirror. What is the nature of the image? What is the nature of the image? Virtual erect and enlarge. Virtual erect and enlarge. Virtual erect and enlarge. Okay. So that is the case. In that case, next one. So name the type of mirror. Name the type of mirror used in following situation. Headlights of a car. In a headlights of the car, what type of mirror we will use? Concave mirror. Side view, rear view mirror. Side view, rear view mirror. We will use convex mirror. So here you can observe, okay. So name the type of mirror used in the following situation. Headlights of a car. In a headlights of a car, what type of mirror will use? Concave mirror. And side view and side or rear view mirror of vehicles. So side view mirror is convex mirror. Solar furnace, concave mirror. Okay, so in solar furnace we'll use concave mirror. Whenever the light rays falls on it, so immediately it will converge the light rays. So that is about mirrors. Mirror related to questions. Mirror related to questions. How can you identify three mirrors? Very very important. One more light ray. Under what conditions concave mirror produce virtual erect and image? Draw a label diagram to show the formation of image. Just now I explained. So object is placed between F and P. And one more thing, if the light ray is passing along the normal line. So if you are taking here, so this is a concave mirror. So I am taking the pole, focus, center of curvature. If the light ray is passing along the normal line, along the principal axis. See here we are taking the principal axis. If the light ray is passing along the principal axis, so angle of incidence is 0, angle of reflection is 0. So angle of incident is 0, angle of reflection is 0, because the light ray will move in the same direction. That's why angle of incident is 0, angle of reflection also 0. Because when the light ray is incidenting along the principal axis, the reflector light ray moves along the same line. That's why angle of incident is 0, angle of reflection also 0. Okay. So next one, we will go to the next one. How can you identify? Very very important. How can you identify the three types of mirrors without touching? Without touching, we have to understand. Without touching, we should not touch the mirrors. Without touching, how can you identify? So in concave mirror, virtual erect and enlarged image will form. In concave mirror, virtual erect and enlarged. So in convex mirror, so I'll see, depending on the nature of the image, we can say what type of mirror it is. If you are taking concave mirror, you see, concave mirror. So virtual erect and enlarged. So if you are taking the concave mirror like this, so this is the point. So this is the pole, focus, and center of curvature. If you place the object here, one light ray I am taking, passes through the focus. Another light ray is incidenting at the pole, it reflects back. So if you are extending these light rays, the image will form here. Okay, so this is a one. Coming to the convex mirror, if you are taking convex mirror, I am considering this is the pole, focus, and center of curvature. So if the object is placed here, one light ray I am taking like this, it will be reflected back. Another light ray I am taking incident at the pole, it will be reflected. So if you are extending this one, the image will form. So here image will form. Whereas the plane mirror, if you are taking the plane mirror, okay. So if you are seeing the plane mirror, in the plane mirror, virtual erect and same size of image will form. So I am taking the plane mirror here. So I am considering object here. One light ray I am taking like this, it passes like this. Another light ray, so it will reflect in the same direction. Okay. So one more light ray I am taking here. It is incidenting at this point. It will be reflected. So one more light ray I am taking here. It will be reflected. So here. So if you are extending these light rays, so here the image will form here. Okay, so I am taking the image. So image will be forming here. Understood? So here in these three cases, without touching the mirror, we can understand. So this is second case and third case. So without touching the mirror, so in first case you can see, in the first case image is virtual erect and enlarge. In the first case image is virtual erect and enlarge. Virtual erect and enlarge. In the second case virtual erect and diminished. Virtual erect and diminished. In third case, virtual erect and same size. Virtual erect and same size. Virtual erect and same size. Understood or not? So very very important. So you need to understand. You need to understand. You have to observe by looking into the mirror. So virtual image is enlarged or not. So then it is concave mirror. Virtual image diminished or not. That is a convex mirror. Virtual image is same size or not. That is a plane mirror. So by that, by this we can understand. So image is virtual erect or diminished, or virtual erect or enlarged, virtual erect or same size. By this we can understand. By this we can identify. Okay, so I hope it is very clear. So this is about coming this is about mirrors, image formation, related to questions, image formations, everything. Yes. And one more last question. That question is, a man is standing in front of the mirror. So related to this only, a man standing in front of a mirror finds his image having very small head. Once again, a man for standing in front of a mirror finds his 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 having a very small head, and a fat body, small head, fat body, and legs are normal size. So small head means convex mirror. So fat body means concave mirror, and legs are normal. Means plane mirror. Once again, a small head. So the person standing in front of the mirror, and looking into the mirror, so he identified. So he having small head, and fat body, and normal size legs, so now we can take small head is convex mirror, fat body is concave mirror, and normal size legs is a plane mirror. I hope it is very clear to all. So this is about mirrors. Now we will discuss about refraction. So refraction. So when the light ray is passing from light ray, so I'm talking about refraction phenomena. We'll discuss refraction. Refraction we are discussing. Refraction is nothing but when the light ray is passing from one medium to another medium. If the light ray is passing from one medium to another medium at the point of interference. So if you are taking refraction. Okay, so refraction, if you are taking refraction, so I'm taking this surface, this is a rarer medium, denser medium, denser medium. If the light ray is moving from rarer to denser, okay, so I'm taking here, so this is the incident ray, so this is the normal line, normal line. So this is the refracted ray, so in angle of incidence, and angle of reflection. So if the light ray is passing from rarer to denser, at the point of interference, light ray will bend towards a normal line. Light ray bends towards the normal line. The point of interference, light ray will bend towards the normal line. So that is called refraction. This is called refraction. So when the light ray is moving from rarer to denser, if the light ray is moving from rarer to denser, at the point of interference, the light ray will bend. Angle of incident is greater than the angle of reflection. Angle of incident is greater than the angle of reflection. So now I am considering angle of incident is greater than the angle of reflection. First one, if the same thing if you are taking, this is a normal line. So normal line I am drawing, normal line I am considering here, normal line I am taking. So here this is the normal line, okay. So if the light ray is passing from this is the rarer medium, denser medium. If the light ray is passing from denser to rarer, normally in this case, if the light ray is moving from rarer to denser, it bends towards the normal line. So angle of incident is greater than the angle of refraction. So the same condition, if the light ray is passing from denser to rarer, so here the angle of incident is here, angle of incident I am taking. This is the angle of incidence, and this one is the angle of refraction. This is the angle of incident and angle of refraction. So in this case, angle of refraction is greater than the angle of incidence. So why we are saying this one? Because so when light ray is moving, in this case, if the light ray is moving from one medium to another medium, so light ray, if it is bending towards the normal line, means speed is decreasing. If speed is decreasing, then what happens? The light ray will bend towards the normal line. Same thing here. If the light ray is moving from denser to rarer, the refracted ray, so in the rarer medium, the refracted ray moves away from the normal line. Why? Because speed is increasing. Here, if the speed is decreasing, that's why the light ray is moving from rarer to denser, it bends towards the normal line. Here speed is increasing, that's why the light ray will bend towards away from the normal line. So here speed is increasing, here speed is decreasing. If light ray is moving from rarer to denser, so what is rarer medium? What is a denser medium? Speed of light is more in the medium, so that is rarer medium. Speed of light is less in the medium, that is denser medium. Suppose example, air and water you take. Air. So speed of light is more. Water. Speed of light is less. If you are taking air and glass, if you take, suppose water and glass you take. Here water, here glass. So in the water and glass, water is a rarer medium. Glass is a denser medium. Water is a rarer medium. Glass is a denser medium. Because so speed increasing or decreasing, it depends. Okay. Next one we are going to discuss about laws of refraction. Laws of refraction means, if you are taking, angle of incident is equal to angle of reflection. So angle of incident is equal to angle of reflection. So laws of refraction is nothing but, so normally if you are taking here, now we consider here, this is about laws of refraction. So here, angle of incident ray, refracted ray, normal line. First point is incident ray, refracted ray, normal line lies in the same plane. Incident ray, refracted ray, normal line. Incident ray, refracted ray, normal line. Is on the same plane, lies in the same plane. So second one, sine of angle of incidence to sine of angle of refraction equal to constant. Sine of angle of incident to sine of angle of refraction equal to constant. So now we are considering sine of angle of incident to sine of angle of refraction equal to constant. That is nothing but sin I by sin r equal to constant. That constant is nothing but refractive index. That constant is nothing but refractive index. Refractive index is nothing but, so here, so with the help of velocity, if you are talking, so refractive index is nothing but speed of light in vacuum by speed of light in medium. Refractive index is nothing but speed of light in vacuum by speed of light in medium. Speed of light in vacuum by speed of light in medium. N equal to C by V. 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 So speed of light in vacuum by speed of light in medium. Okay, na? So speed of light in medium. So we are considering now. So n equal to C by V, n equal to C by V, n equal to C by V, n equal to C by V. Yes, Snell's law. N equal to C by V, n equal to C by V. Speed of light in vacuum or air by speed of light in medium. Speed of light in vacuum or air by speed of light in medium. So n equal to C by V, n equal to C by V, n equal to C by V. So speed of light in vacuum equal to 3 into 10 power 8 meter per second. 3 into 10 power 8 meter per second. So C I am considering 3 into 10 power 8 meter per second. 10 power 8 meter per second. So very, very important value we have to remember. So speed of light in vacuum or air is speed of light in vacuum or air is speed of light in vacuum or air is 3 into 10 power 8 meter per second. So that is nothing but so C equal to 3 into 10 power 8. That is nothing but refractive index. That is nothing but absolute refractive index. Not only refractive index, absolute refractive index. N equal to C by V. N equal to C by V. Absolute refractive index equal to N equal to C by V. Whereas relative refractive index is there. Relative refractive index is, so speed of light in vacuum, speed of light in medium 1 by speed of light in medium 2. Speed of light in medium 1 by speed of light in medium 2. So here I am considering one more point. So refractive index, if you are taking 1 to 1, so we can also write N2 by N1, that is nothing but V1 by V2, because N is inversely proportional to velocity. N is inversely proportional to velocity. So so if you are taking like this, N is inversely proportional to velocity. Hi Narsi, how are you? Okay, so N is inversely proportional to velocity. N is inversely proportional to velocity. Okay, top notch. Hi. So, hi everyone. Welcome to the class, student the brand. Thank you so much for joining and attending and listening the class. Happy to see you all. Okay, come to the point. So N is inversely proportional to velocity. N is inversely proportional to velocity. Refractive index is inversely proportional to refractive index is inversely proportional to velocity. Refractive index is inversely proportional to velocity. So now we are considering N12. N12 equal to N1 by N2. N1 by N2. That is nothing but V2 by V1. V2 by V1, V2 by V1. So I am considering here N21 equal to N2 by N1, that is nothing but V1 by V2. Whereas, so because N is inversely proportional to velocity, N is inversely proportional to velocity, N is inversely proportional to velocity. So N12 equal to N1 by N2 equal to V2 by V1. So refractive index, relative refractive index is nothing but Relative refractive index is nothing but speed of light in medium 1 by speed of light in medium 2. Speed of light in medium 1 by speed of light in medium 2. That is nothing but yeah. Thank you so much. Definitely I will. Thank you, Amulya. Okay, so here I am considering here. So n is inversely proportional to velocity. N is inversely proportional to velocity. So n2 by n2 n2 1 if you are taking n2 1 if you are taking here n2 by n1 equal to v1 by v2. So here n1 2 if you are taking n1 by n2 equal to v2 by v1. So it is relative refractive index, relative refractive index, relative refractive index, relative refractive index, right? Relative refractive index. So the speed of light in medium 1 by speed of light in medium 2. Speed of light in medium 1 by speed of light in medium 2 is called relative refractive index. Whereas absolute refractive index, absolute refractive index is so speed of light in vacuum by speed of light in medium. Speed of light in vacuum by speed of light in medium. Speed of light in vacuum by speed of light in medium. C is nothing but 3 into 10 power 8 meter per second. 3. So C values speed of light in vacuum is 3 into 10 power 8 meter per second. 3 into 10 power 8 meter per second. So N equal to C by V. 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 So relative refractive index if you are taking relative refractive n2 1 equal to n2 by n1 v1 by v2. N is inversely proportional to velocity. N1 equal to n1 by n2, that is about v2 by v1. So this is about relative refractive index. So based on this one, few problems will discuss now. Okay, so let's discuss few problems, then I'll explain about so we'll see. Related to refractive index. This question already I did, but still I want to discuss these questions. Very, very important question. So in the list, so what is meant by refractive index? Refractive index. Refractive index question mark. So if the speed of light in vacuum, speed of light in a medium, speed of light in a medium is 2 by 3 of the speed of light in vacuum, speed of light in vacuum, find the refractive index, of that medium. So this is one question. Okay, so one more question I am giving, so you can solve this one. So one more small question. N12 into N21, how much? So these are the two questions. I'm giving. Okay, try to solve it. So explanation I will give now. 10-7. So I'll start 10 explanation. at the rate of 10, 10, 12 p.m. 5 minutes I'm giving. 5 minutes. So after 5 minutes I'll explain. After 5 minutes I'll explain. Okay. These two questions. After 5 minutes I'll explain. So just check it once. Okay. So go through it. Okay. Sorry for it. Timings. Actually here the time is 11:10. I mentioned 10. Okay. Sorry for that. You can take it 11, 11, 12. I hope you can understand. Sorry for it. Okay. So 11 just for changing I came. 11, 12. One more minute. Anyway, I'll drink water and come. Okay. Check it once. Okay, so let's do the problem. Now exactly 11, 11 12, right? Now you see here, so now you can see this problem I'll explain. This problem I'll explain. So this problem is, if you are doing this problem, n1 by n2 into n2 by n1. So this will get cancelled, this will get cancelled, 1. The answer is 1, right? So answer is 1 in this case. Answer is 1. Coming to the next one. Coming to the next one. So next problem. So this problem will do it. This problem will do it. I hope you got the answer for this, right? Yes. Okay. So here you can observe what is meant by refractive index if the speed of light in medium is, so 2 by 3 of speed of light in that vacuum. Okay. So the refractive index of medium is, find the refractive index of medium, they're asking. Refractive index of medium. Okay. So in that case, we have to follow one thing. First write the formula. Okay, first write the formula of refractive index. So n equal to C by V. Solution. N equal to C by V solution. So they mentioned, so like here the refract. So the speed of light in medium. The speed of light in medium is 2 by 3 of speed of light in that vacuum. So V equal to 2 by 3 of C. So V equal to 2 by 3 of C. So N equal to C by 2 by 3 into C. So C get cancelled. Then if it is goes N equal to 3 by 2, that is nothing but 1.5. So 1.5. So refractive index value is 1.5. Refractive index value is 1.5. I hope you got it. So I hope it is very clear. To you all. Okay. So like that we can do it. So that is about refractive index. Okay. So next one, this value also given. One more condition, one more statement they given related to statement questions. The refractive index of diamond is 2.42 times faster in vacuum than in diamond. The refractive index, the statement. Okay, so the refractive index of diamond is 2.42. Okay, so the refractive index of diamond is 2.42. What is meaning of this statement? This meaning of the statement is, so light travels 2.42 times faster in air than in medium, than in diamond. Okay, so speed of light is 2.42 times greater in air than in diamond. So that's the meaning. So we can see next one, where we'll go to the refractive index. I explained. That's enough. Next we'll go to the laws of refraction. Laws of refraction also completed. We'll go to the refractive index, that is nothing but this also completed. Glass lab I will explain. Glass lab. After glass lab we'll go to the image formations of convex lens. So now you are considering, now you are taking now you are taking glass lab. So glass lab I am taking, this is a glass lab. So if you are taking like this, so incident ray is passing like this incident ray. So glass slab surface must be like this. So incident ray I am taking here. This incident ray. So light is incidenting on it. So I am taking this normal line. Normal line. Refracted ray. So I am taking this dotted line. So you are taking this emergent ray. Okay, so this is about incident ray. Incident ray. Refracted ray. This is a refracted ray. This is the emergent ray. Emergent ray. So this is the air. Air I am taking air. Glass slab. Glass slab. So air and glass slab. So if you are extending this incident ray, this is the incident ray, right? So this is the incident ray. If you are extending that incident ray, the light ray passes. The light ray passes, okay, along like this. I'm taking here. So the distance between emergent ray and the distance between emergent ray and extended incident ray is called lateral shift. Lateral shift. Lateral shift. The distance between emergent ray and incident ray. So initial direction of the incident ray is called lateral shift. Yeah, I'll teach for class 12 also. You can see if any details are required, so you can contact to this number 984981280 984981280. So this is the number. Okay. So come to the point. Next one. So this incident ray, refracted ray, emergent ray. Incident ray, refracted ray, emergent ray. Incident ray, refracted ray, emergent ray. So we are extending the incident ray. So distance between emergent ray and extended incident ray is called lateral shift. Lateral shift, okay. So this is the angle between incident ray and normal line is called angle of incident. Angle between refracted ray and normal line is called angle of refraction. Angle between emergent ray and angle between emergent ray and normal line is called angle of emergence. Angle of emergence. Once again, angle between incident ray and normal line is called angle of incident. Between incident ray and normal line is called angle of incident. Angle between refracted and normal line is called angle of refraction. Angle between emergent ray and normal line is called angle of emergence. Angle of emergence. Angle of emergence. Angle of emergence. Okay. So angle of emergence. So lateral shift, the distance between emergent ray and incident ray. So the vertical displacement or perpendicular distance between emergent ray and so incident ray is called lateral shift. Lateral shift. If you are taking one more, so I'm considering here, I'm taking the beaker like this. I'm taking the beaker. So here I place the coin. So I'm placing the coin. Okay. So I'm placing the coin. This is the coin. This is the coin, I hope. This is the coin. Okay. So coin I placed. Coin. This is the coin. Coin. Okay. So if you are standing here at this position, so you can't able to see the coin at this position. You can't able to see the coin at this position. You can't able to see the coin. So when you like, so normally if you're taking, okay. So before pouring water, sorry. So after that it's poured. So first you have to place the coin at the bottom of the beaker. At the bottom of the beaker. So in this position you can't able to see. So after pouring water, okay. After pouring water, the coin positions will rises up. The coin position will rises up. The coin position will rises up. Okay. So the distance between. So this position is called apparent position. Apparent position. Apparent position, and this position is called actual position of the coin. Okay. So this apparent position of the coin, this actual position of the coin, the distance between actual position to apparent position of the coin is called the distance between actual position to apparent position is called vertical shift. Is called vertical shift. Is called vertical shift. The distance between actual position to apparent position of the coin is called vertical shift. The distance between actual position to apparent position of the coin is called vertical shift. 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 The distance between actual position to apparent position of the coin is called vertical shift. The distance between actual position to apparent position of the coin is called vertical shift. I hope it is very clear to you all. So next one, even if you are placing the so I Meena Verma, so if you are placing the so inside of the beaker, if you place 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 the lemon, if you place the lemon inside of the beaker, if you place the lemon, okay, so if you place the lemon, it appears bigger, because of the refraction, when you place the lemon inside of the beaker, it appears bigger. Even pencil, if you are taking the pencil here, I'm taking the pencil, water is here, water I'm taking here, water I'm considering here, okay, water I'm considering. So when you're taking the pencil here, when you're taking the pencil like this, okay, at this position, at the point of interference, at this position, at the point of air and water, so the pencil appears here. The pencil appears to be bent. Actually, the position is normally only. So even if you place the pencil like this, if you place pencil, okay, normally pen or pencil, if you place at this point of air and water, so the pencil appears to be bent. Actually, it won't like that, it won't bend, but it appears because of the refraction, the pencil appears to be bent. Okay, pencil appears to be bent. Okay, this is about lemon. If you place inside of the water, lemon placed inside of the water, it appears to be bigger. So pencil appears bent at the interference of the water and air. And if you place the coin at the bottom of the beaker, so initially we can't able to see. Late, after pouring water, the coin appears to be rise. The coin position appears to be rise. So we can see, by this we can see the distance between the vertical distance between so apparent position to actual position of the apparent position to actual position of the coin, 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 apparent position to actual position of the coin is called vertical shift. 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 The distance between apparent position to actual position of the coin. Here, this is the apparent position, this is the actual position, apparent position, actual position, apparent position, actual position. So this is the vertical distance. The vertical distance between apparent position to actual position is called apparent position to actual position is called apparent position to actual position is called vertical shift. Vertical shift. Vertical shift. Vertical shift. Vertical shift. I hope it is very clear to you. Next one. We are going to the next one. So that is about lens. We are going to discuss about lens. So now we'll discuss the lens. Okay. So now you are considering here, I am taking the convex lens, convex lens. So ray rules of convex lens, ray rules of convex lens. Convex lens and concave lens also will draw. Convex lens and concave lens. The ray rules of convex lens and concave lens. So I am taking here, this is a convex lens, optic center F1, 2F1, F2, 2F2. So this is about convex lens. This is about convex lens. Okay. So F1, 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 2F1, optic center F2, 2F2. So first ray rule is, so light ray is coming from infinity. After refraction passes through focus. Light ray is coming from infinity. So light ray is coming from infinity. So I am taking here. Light ray is coming from infinity. This is F2. Light ray is coming from infinity. After refraction passes through focus. Second one. So optic center F1, 2F1, F2, 2F2. Light ray is passing through focus. After refraction become parallel to the principal axis. Third one, light ray is passing optic center. Light ray is passing through optic center. So optic center F1, 2F1, F2, 2F2. So light ray is passing through optic center. So no deviation takes place. No deviation takes place. Okay. So next one you are saying concave lens. First one concave lens. Concave lens. So I am taking here optic center F1, 2F1, F2, 2F2. So one light ray is coming parallel to the principal axis. One light ray I am taking parallel to the principal axis. After refraction it diverge. After refraction it diverge. So if you are extending, it passes through the F1. Next one. So if you are taking here optic center F1, 2F1, F2, 2F2. Light ray is passing through the focus. After refraction it will be passing parallel to the principal axis. Coming to the third one. Optic center F1, 2F1, F2, 2F2. Light ray is passing through optic center. So no deviation takes place. So first one you are considering here. Rachi, hi. Okay, so light rays coming parallel to the principal axis. After refraction it diverge. Light rays, so one more light ray is incidenting after refraction passes parallel to the principal axis. So one more light ray passing through the optic center. No deviation takes place. No deviation takes place. I hope it is very clear to all. Next one. So next one will go to the one more. Next one will go to the one more, that is ray rules of image formation by convex lens. Image formation by convex lens. We'll discuss image formation by convex lens. So one letter I am taking here. Marco. So first one I am taking here. So convex lens. Convex lens. So optic center F1, 2F1, F2, 2F2. So convex lens F1 to F1, F2 to F2. So how many light rays are required to form the image of the object? How many light rays? Minimum 2 light rays are required to form the image of the object. Minimum 2 light rays are required to form the image of the object, right? So I am taking one light ray. So here one light ray I am taking like this. After refraction passes through focus. Another light ray I am taking like this. So after refraction it passes. Okay. So now you are considering here object is at infinity. Image will form at f2. Nature of the image is real and inverted. Nature of the image is real and inverted. Nature of the image is real and inverted. Size of the image is highly diminished. So highly diminished. Point size image is forming at focus. So one light object is placed at infinity, image will form at f2. So nature of the image is real and inverted. Size of the image is highly diminished. Size of the image is highly diminished. So coming to the next one. Next one I am taking here. Optic center f1, 2f1, f2, 2f2. So object is placed here beyond 2f1. Object is placed beyond 2f1. So how many light rays? As I said, minimum 2 light rays are required to form the image of the object. How many light rays are required to form the image of the object? Minimum 2 light rays are required to form the image of the object. Yes or no? Minimum 2 light rays I said. So here you can see I am taking one light ray. Okay, minimum 2 light rays I said. So one light ray I am taking like this. It passes through the focus. So after refraction it passes through the focus. Another light I am taking through the optic center. So those will meet between f2 and 2f2. Between f2 and 2f2 here image will form. Image will form here. This is the 2f2. This is f2. Image will form here. Object is beyond 2f1. Object is beyond 2f1 here. Object I placed. Object is placed beyond 2f1. Beyond 2f1. Image will form between f2 and 2f2. Nature of the image is real and inverted. Nature of the image is real and inverted. Coming to the size. Nature of the image is real and inverted. Nature of the image is real and inverted. Nature of the image is real and inverted. Size of the image is diminished. Size of the image is diminished. Compared to the object, image size is decreased. 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 So image size is decreased. So diminished. And next image formations. Second image formations I'm taking here. Optic center f1, 2f1, F2, 2F2. So object is placed at 2F1. Object is placed at 2F1. So image will form. Image will form here. Image is forming. So here F2, 2F2. So one light I am taking like this. It passes through the focus. One light I am taking. It passes through the focus. Another light I am taking through the optic center. So both will meet here. So object is at 2F1. Object is at 2F1. Okay. Object is at 2F1. Object is 2F1. Image also will form 2F1, 2F2. Nature of the image is real and inverted. Size of the image is same size. Same size. So coming to the, this is third. Coming to the fourth one. Object is placed between 2F1 and F1. Object is placed between 2F1 and F1. So now you can see. So this is the optic center. F1, 2F1, F2, 2F2. Object is placed between 2F1 and F1. If you are placing the object here, how many light rays are required to form the image of the object? Minimum 2 light rays. As I said, minimum 2 light rays are required to form the image of the object. Minimum 2 light rays are required to form the image of the object. Yes or no? Minimum 2 light rays are required to form the image of the object. Okay. So one light ray I am taking here. So this is one light ray. So after refraction it passes through focus. Another light ray I am taking here. So it passes through optic center. So those will meet beyond 2F2. So image will form here 2F2 here, 2F2. So the image will form here. Object is between 2F1 and F1. Object is placed between 2F1 and F1. Object is placed between 2F1 and F1. Image will form beyond 2F2. Image will form beyond F2. Once again, object is placed between F1, 2F1 and F1. Image will form beyond 2F2. Nature of the image is image is between beyond 2F2. Beyond 2F2. Nature of the image is real and inverted. Size of the image is large. Compared to the object, image size is increased. 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 I hope it is very clear to you all. So next one. So we'll go to the last two image formations. So we'll go for next two image formations. Okay. So here consider fifth one. Object is placed optic center F1, 2F1, F2, 2F2. So object is placed at F1. One light ray I am taking like this, it passes through F2. Another light ray it passes through optic center. So object is F1. Image will form at infinity. Nature of the image is real and inverted. Size of the image is highly enlarged. Last case is very important. We'll discuss last case between 2F1 and F1. So beyond 2F2, real and inverted. Nature is enlarged image. Okay, so I'll draw the last case. You can check here. Last case. Sixth case. optic center F1, 2F1, F2, 2F2. Okay, na? So if the object is placed between F and O, here see. So last case is very important. Object is placed between F and O. One light I am taking like this, it passes through focus. Okay, another light I am taking, it passes through optic center. So if you are extending this light rays, those light rays will meet the image will form same side of the object. So this is the last case, sixth case. Very, very important this case. So 3 marks question they will ask in the exam. Definitely they will ask. So make sure that you are learning this one. Okay, very, very important for 3 marks. For 3 marks, very, very important. Okay. Just check once. Object is placed between F1 and O. F1 and O. Image will form same side of the object. Same side of the object. Nature of the image is virtual erect and nature of the image virtual erect and enlarged. Nature of the image is virtual erect and enlarged. I hope it is very clear to all. So one check all the image formations, all the image formations. Once check 11:45 now. Okay, so we can take just check the diagram. Explanation I'll give once again from 11:50 explanation at the rate of 11:50 p.m. Okay, so I'll explain once again. So remaining points, check once. Meanwhile, you can check this diagrams. So practice once. Okay, so be ready for explanation. Now I hope it is completed. Convex lens completed. Now we'll discuss about concave lens image formations. Concave lens image formations we'll discuss. Okay, so let's start. So concave lens, the convex lens. Concave lens only two image formations are there. Concave lens only two image formations. Only convex six are there according to the object positions, image position. Okay, so nature according to that it depends. But concave lens only two image formations are there. Concave lens only two image formations. Concave lens only two image formations. We'll discuss those one. Okay, so let's discuss. Okay, concave lens only two image formations. First one, optic center f1, 2f1, f2, 2f2. So concave lens, we are discussing about a concave lens. Concave lens. Concave lens. One light ray I am taking here. So if the light ray is passing like this, one light ray I am considering here. After refraction, so it will passes like this. One more light ray I am taking like this. If you are extending these light rays, the image will form here. Object is at infinity, image will form at f1. Nature of the image is nature of the image is nature of the image is object is at infinity, image will form at f1. Nature of the image is virtual, erect and diminished, or highly diminished. We can say highly diminished. Image will form at focus, right? So second one, if you are taking optic center f1, 2f1, f2, 2f2. So object is placed anywhere between infinity and object is placed. So one light I am taking like this. So one more light I am taking. It passes through optic center. If you are extending this light ray, the image will form. Object is between optic center and infinity. Image will form between f1 and o. F1 and o. Nature of the image is virtual erect, diminished. So in the both the cases you can observe, in the both the cases always virtual erect and diminished image will form. In both the cases always. So in concave lens if you are taking, even on a convex mirror, here in concave lens there convex mirror, in the convex mirror case and concave lens. Okay, so in these two cases, always virtual erect and diminished image will form. So compared to the object. Okay, so now we are going to the, I hope already everything is completed. Image formations. Lens formula is power of lens. Power of lens we'll discuss. Power of lens is nothing but reciprocal of focal length. P equal to 1 by f. The degree of converging or diverging of lens achieved is known as power of lens. The degree of converging of converging or degree the degree of converging or diverging of lens achieved is known as is known as is known as power of lens. P equal to 1 by f. P equal to 1 by f. P equal to 1 by f. Okay. So SI unit of power of lens is diopter. Power of lens is positive for convex lens. Power of lens is negative for concave lens. Power of lens is positive for convex. Power of lens is negative for concave. So lens formula 1 by f equal to 1 by v minus 1 by u. Lens formula 1 by f equal to 1 by v minus 1 by u. Magnification equal to magnification, if you are taking magnification equal to height of the image by height of the object. So v by u. Okay, so this is about magnifications, mirror lens formula, magnification, power of lens, degree of converging or diverging of lens achieved. P equal to 1 by f. Power of lens is positive for convex lens. Power of lens is negative for concave lens. Okay, SI unit of power of lens is diopter. And uh, and that's enough. So I hope almost we discussed everything. Okay, so we'll see. Any few questions are left. We'll work out. So we'll turn the page. We'll see. Any questions are left or. If the light is passing along the normal line, okay. I'm taking here also. Okay. So here. So if anything is required, you can contact to this number 9849812804. This is the number. So if you contact, we'll discuss. Any concerns are there? Any doubts? Any discussions? Okay. Okay. Under what conditions? So here. So under what conditions? Under what condition will a glass lens placed in a transparent liquid becomes visible? When the refractive index of glass lens and liquid are same, glass lens or liquid are same, then the glass lens will become invisible in the liquid. So if you place a glass slab in a liquid, so both refractive index is same, then then so the glass slab will not be visible, right? Yes. Next, lenses related to lens. I hope all we completed. Uses of lenses are there. So use of convex lens. I have to show the convex lens here. Convex lens. This is a convex lens and concave lens designed and crafted by me, by Shiva sir. Convex lens. This is a convex lens. Convex lens. Is it good? Convex lens. You can see here. Convex lens. Right? And you crafted it. Next, concave lens. This is a concave lens. Next, concave lens. Concave lens. This is concave lens. concave lens and convex lens. I hope it is not visible. Just check once. Convex lens and concave lens, both. So I did like this. Okay, so to see the, so by seeing immediately we can recognize, okay, in a big manner if it is there. By seeing immediately we can get to know, right? Understood? Yes. Thank you so much. So I hope it is very clear to all. Next one. Okay, so that's enough. That is about convex lens, concave lens, image formations, lenses uses. I said no. Convex lenses are used in spectacles to correct the defect of vision hypermetropia, long-sightedness. Convex lens used for making simple camera. Convex lens used are magnifying glass. That is pharmacist, dentist, watchmaker, pharmacist, and watchmaker. And concave lens are used in spectacle to correct the defect of vision called myopia, short-sightedness. Concave lens is used in as eye lens in Galileo telescope. Concave lens is used in wide-angle spy hole indoors. Okay, so that's about. Actually, I sung the song, right. I created songs, everything. Yes, sir. So that's only related to this one. Uses applications only. Myopia, myopia, myopia. Myopia, myopia, myopia. Near distance we can see ya. Far distance we can see ya. Myopia, myopia, myopia. For that correction we are using. Bro, what bro? For that correction we are using concave lens, concave lens, concave lens, concave lens. Hypermetropia, 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 hypermetropia. For a distance we can see, near distance we can see. Hypermetropia, hypermetropia. For that correction, we are using convex lens, convex lens, convex lens, convex lens. Hypermetropia, 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 hypermetropia. Convex lens, convex lens. So now we are going to the one more formula. New Cartesian sign convention. New Cartesian sign convention. All distance are measured from the pole. Distance are positive along the instant trace. Distance are negative opposite to instant trace. Distance are positive above the principal axis. Distance are negative below the principal axis. New Cartesian sign convention. New Cartesian sign convention. According to the sign convention, so we are taking, that's the reason lens. Uh, so I have negative value magnification. No, lens positive. In mirror formula, mirror lens formula. So lens formula will get negative. Mirror formula anyway positive. Magnification will get negative. Lens formula negative. Magnification is positive. Okay, so that's enough for today class. So we'll discuss tomorrow. If you like this content, do like, share, and subscribe to Student the Brand. Thank you so much for joining and attending and no, so listening the class. So with a lot of patience. Thank you so much for your no attending class. So I already said anything you want to discuss, just you can go through this number. We can discuss more points. That is about 9849812804. Okay, so please do interact with me through that number. So this is your Shiva sir from Student Brand signing off. Thank you so much. Namaste.